Okay, guys, this is a pre-lab video lecture for GSI 121. This is Dr. Warner. I've been getting some feedback regarding some of the sort of pre-lab content. Now, the pre-lab content that you've been looking at so far in this lab has basically been the same pre-lab content that we would have had available for you, but I've heard you loud and clear that you would like a little bit more background information now that you're home and online and don't have access to the TAs and things. So in the last lab, mass wasting lab, I also produced a pre-lab lecture, and now I thought I would do the same for this week's lab, which is shorelines, or as this is titled, coastal processes. Now this is just a relatively short lecture. I've also included 3 YouTube videos that do a really good job going through these processes well. One of them, the Beach River of Sand, a relatively old one, but still a pretty solid one, is one that you absolutely must watch before you start doing this lab. And at the very bare minimum, watch that and listen to this one. And there's 2 others that'll help you as well. So hopefully you have enough supporting information to guide you through today's lab. So the point of today is to try to understand some of the nuances behind what creates the sort of diversity that we see in coastal landforms and coastal processes. We're also going to talk about how humans have influenced this process, or how try to influence this process, in many cases to allow ourselves to build on these beautiful coastlines. But one of the key take-home messages of the lab is that coastlines are incredibly transient features, meaning they change very rapidly based on all sorts of different processes that we're going to explore in this lab. And so in many cases, we have to do all sorts of crazy things to keep our coastal communities safe and keep them from falling into the water, essentially. So we can have anything from broad sandy beaches, which is really going to be the focus of much of the lab today. These are the types of sandy beaches you're used to seeing on the east coast of the United States, in New Jersey, and in Long Island, and at least the southern part of Long Island, and of course down through Virginia, North Carolina, and so on. But there are also lush, swampy wetlands that are associated with some of these places that are protected from the waves, places behind some of the barrier beach islands. There are some places that have been drowned by climate change. In other words, the overall rising of the sea levels has actually swamped some of the coastal beaches and coastal regions and have actually drowned some of the river valleys. And then finally, there's a whole set of coastlines on what we call active margins, and I'll talk about what that means later, that are affiliated with really steep, impressive cliffs like you see down here in the lower right corner. Okay, so first and foremost, before we get into beaches and things, the largest supplier of clastic sediment to the oceans are rivers. Okay, now the waves certainly will attack the coastline and erode rocks that are just sitting there on the coast. But the biggest supplier of loose clastic sediments is actually from rivers. And so this is just a top-down picture showing a river coming out to the coastline. Once it reaches the coast, it drops all of its sediment load. And then when it drops its sediment load, it basically spreads out, the river spreads out in all directions and creates what's called a delta. So this is a river delta right here. And so the sand that you're seeing, which is in this case color-coded with a yellow and orange, the sand you're seeing can be moved from the mouth of the delta to form beaches like you're seeing over here. And we'll talk about how you can transition from a delta to a beach like this. Where does the sand that makes the beautiful beaches we're used to, where does this actually come from? So here's just a picture of the Mississippi River Delta. It's a famous delta. You can see the Mississippi River here meandering its way down. It slows down and decelerates when it hits the ocean, drops its sediment, starts to branch off in different directions, and basically produces this really beautiful, what we call bird's foot delta. It almost looks like a bird's foot is where that comes from. Okay, so again, if you look at the ocean water here, you'll see these little sort of sediment plumes that are being carried off by some currents that then supply us with beaches. Okay, so let's first get into one of the biggest processes that will modify and carry sand, and that of course is waves. So waves, the height and the length of the waves, the size of the waves, and what their wavelength is, which wavelength is measured from crest to crest on a wave, as you can see here. Okay, the scale essentially of the waves is all dependent on the wind speed. So waves are generated by wind, how long the wind is actually operating, the distance over which the wind travels, which is what's known as fetch. So if you have strong winds that go for a long time and travel a large distance, you can build up pretty large waves. So this is just a diagram showing the general sort of motions that are going on under the water when a wave actually forms, and they form these rollers here, as we call them. Okay, just going like basically like that, and they're circular in shape when they're not being affected by the land. Okay, and as you'll see in this picture, the sort of scale of those rollers that are going on, okay, here, we actually call them orbitals, wave orbitals, is actually much larger at the top near the surface where the wind is actually interacting, and then the vigor and size of this sort of rolling motion in the water actually decays as you get deeper until you reach something called the wave base. Below the wave base, you don't feel any effect of the waves. If you're above the wave base, you're being sort of sloshed around by these rollers that are moving through the water. Okay? So in today's lab, there's a couple terms that I want you to be aware of. There are two different general kinds of waves. One's called an oscillating wave, and these are when the wave orbitals are circular. So if we go down to this diagram, as the waves approach the shore, they actually do something kind of interesting. So while they're out in open sea and the wave base is not touching the bed, okay, there you have these circular orbitals, and that's called an oscillating wave. Okay. Out here, the wave base, the depth down to that base, is equal to 1/2 the wavelength of the wave. So the wavelength is measured from crest to crest. So this depth is 1/2 that crest to crest wavelength. So you can actually make those measurements by just looking at some pictures, and you'll do that in the lab. A translational wave, on the other hand, is a wave that starts to interact with the seabed. So as the waves approach, and you'll notice this dashed line represents the wave base, eventually it shallows and you actually hit the seabed. And the frictional speed the friction that occurs between the base of the wave and the bed causes the wave to slow down. But the wind is still pushing it at the top, so what happens is the wave starts to bend over like this. Starts to bend over, and eventually it oversteepens and collapses to make what we call wave breakers, okay, right here. Right? We call this set of waves that interact with the seabed translational waves. They basically translate or slide over on top of each other. Okay? And here's just that in text here. You can read all of that stuff, as I just said. One interesting thing, the breaker zone occurs when the wave base is 1/20th of the wavelength. So you can also determine when you might see breakers based on the wave size as well. Okay? All right, now what's interesting here is that once the waves hit and break and hit the coastline, they swash upwards onto the beach face where they will deposit sand, and then gravity will pull that sand back down in what's called the backwash. Okay, so we have swash, backwash, swash, backwash. Now, according to this pattern, the wave's hitting dead straight onto the beach, so swash goes up, backwash comes back, and that's it. However, waves very rarely hit the coast dead on. And so in this diagram here, they're showing sort of the pattern of swash and backswash if the wave crests actually hit at an angle. Okay, so here we have the wave crests aligned at an angle to the coastline. And as those waves come into the coastline and slam into the coastline, okay, so let's look at these arrows here. What you're seeing here in the dark gray is the water. What you're seeing here in the tan is the beach. Okay, and the arrow represents the swash. So if it's coming in at an angle, it swashes up onto the beach. And once it gets high enough, gravity will pull it down. Gravity just pulls it straight down the slope, and it goes like that. Okay. Now, if you look at the accumulative effect of this, you've got swash, backwash, swash, backwash, swash, backwash. Imagine a grain of sand being pushed up the beach like this, falling back down into the water, then being pushed back up by the waves again, falling back down in the water, up, down, okay? That grain of sand is going to have a net motion from going left to right across this diagram. And so if you look down here at this diagram, that's this arrow showing that longshore, as it's called, current. The swash backwash creates a longshore current that moves parallel to the coastline and moves sand in that direction. We call the sand motion longshore transport or longshore drift. Basically, the sand is drifting along the coastline. The current is the actual movement of the water itself. So this is a fundamental process for affecting beaches because once the sand comes out of the delta and gets on the coastline, the longshore current will transport that sand along the coast, building all sorts of interesting beach faces. Okay, so we have an example here of a nice beach there. We have these features coming out I'm going to show in a minute. These are called spits, but basically these are extensions of that beach due to the longshore drift, okay, pushing the sand further and further this way. In places where we have a little detached beach like this that basically blocks off the open ocean from some backwater area called a lagoon, this is called a barrier beach island. Okay. In other places, if you look over here, here's a spit, again, Baymouth Spit. This particular spit is growing across this bay. Okay, we're going to talk about what estuaries are in a minute. And eventually, it's possible that that spit will completely close off that bay and we get something called a baymouth bar. Okay, it's basically blocking this bay behind it with sand. You're going to be exploring all these different possible features in the lab today. Okay, so you're going to look at beaches, sandbars, sand spits, barrier islands, all sorts of interesting things. So here's just a picture of a nice barrier island. Here's sand that has been accumulating due to longshore drift in this area. It's also often generated by longshore spit migration as well. And what's interesting, this is the open ocean. The area behind the beach we call a lagoon, in case you were wondering. This is an area where very low wave action, an area where mostly just tidal forces affect the water. Remember, all the ocean is affected by tides. The gravitational pull of the moon causes a high tide and a low tide, high tide and a low tide. We're not really talking about that in this lab. Oops, but that is another important process that's going on here. Okay, I did want to mention tidal flats very quickly. So in regions, for example, that are cut off from stronger ocean waves, like for example this lagoon behind the barrier island, this estuary here, an estuary is basically a valley, a submerged river valley, okay, filled with water. This area is protected from open ocean waves. This area is protected from open ocean waves. So behind barrier islands or estuaries, we get really, really, really slow water. Water's not moving very fast. And here we just get what are called tidal flats. These tidal flats don't really have a lot of sand. They're mostly comprised of really low energy mud. Okay, things like silt and clay. Okay, so really we call them mud flats. Again, those occur in areas protected from the waves. Here's just a picture of low tide on a mud flat. This is basically literally a step in this is just mud. Here's people falling in mud. This is what a mud flat looks like. Okay, now if waves were here, waves would pick this mud up and just transport it right out. So again, these are areas protected by the waves. Here's an estuary, and an estuary again is a river valley that enters into the ocean. However, this particular river valley is being submerged by the ocean. This is usually related to the rising sea level associated with a couple things. The sea level rose most recently over the last 10,000 years due to melting of the ice sheets. Okay, there was about 10,000 years ago to about 2 million years ago, there was an ice age, and ice sheets grew down from the North Pole all the way down to New York State. We were covered in glaciers here. Once that ice melted, that water went back into the ocean and the sea level rose. And so many of the rivers in the world, their valleys are submerged where the river meets the ocean. Okay, here's an area then where we're protected from waves, protected from the open ocean, so we have these mud flats. Okay. The other reason, of course, in some places where you're getting submerged, smaller creeks and things, is due to the more recent climate change, the spike in warming and the spike in sea level rise that's related to anthropogenic activities, to humans. Okay, now those coastal morphologies that I just showed you are very familiar to us. They are things that we're used to seeing along the east coast of the United States. So where my cursor is right here is the east coast of the US. Okay, that's things like the Long Island coast, the New Jersey coast, and so on and so forth. However, that type of morphology, that type of shape, as that word refers to, is most common for coastlines that occur very far away from plate boundaries. Okay, so here's the nearest plate boundary for us in the east coast of the United States, and it's the mid-ocean ridge. that's going right down the Atlantic Ocean. That's our closest plate boundary. In many ways, the San Andreas is almost closer, but really that is the closest plate boundary to us. On the west coast of the United States, however, they're right on a plate boundary. Today you're going to actually examine one that's up here by what's called the Juan de Fuca plate. It's not the San Andreas, it's a different plate boundary just next to Washington State and Seattle. So the west coast looks very different. So while this is our east coast, very flat lying area, we have barrier islands and lagoons and mud flats and tidal flats. This is what the west coast looks like. This is the Pacific coast in the Oregon area. And here you see bedrock cliffs. You see sea stacks, as they're called. So these two coasts are very different in morphology, and we're going to talk about why in the lab today. Okay. So what do we mean by passive margin? The east coast of the U.S. is a passive continental margin. We're at the edge of the continent. Technically, the continental crust ends here at the continental slope, which leads down into the abyssal plain, which is the bottom of the ocean. That's actually true oceanic crust. Up here in the continental shelf is true continental crust. Up here. Well, on the East Coast, you're going to do a profile today across New Jersey, and you're going to see that this is incredibly flat terrain here. The continental shelf is very flat, very broad, and the beaches and the landscape are very flat and very broad. Okay, so this is kind of the nice profile drawn out for you here. Here's the continental crust, here's ocean crust, and there's that slope leading down into the abyssal plain. So we get broad, long, flat beaches and flats comprised of loose sediment. There's a broad continental shelf on which that stuff rests. Okay, here's a topographic profile that I'm going to save. You're going to make something like this in Google Earth. So I'm not going to talk much about this, but basically you're going to calculate the gradient of the New Jersey coast down into the Atlantic Ocean. And gradient is the change in elevation with distance. And you're going to have to calculate that with the negative numbers. We're going to go underwater to calculate our gradient as well. Now, if we go to the west coast of the United States, this is an active margin. Okay, so we're right next to a plate boundary. That means tectonically we're experiencing things like tectonic uplift. We're experiencing mountain building. And that has a very dramatic effect on the coastal features. So first off, on the west coast we have a very narrow continental shelf, which is very typical of an active margin. In this case, the shelf is only 20 kilometers wide. In the case of New Jersey, if we go back a couple, it was 200 kilometers wide. So that's a big difference right there. Okay. There's very steep sloping topography, not just on the landscape here where you have mountains, you can see in California, but also down the continental slope itself. You get these really steep canyons that basically form off of the continental slope. And what results from this is many of the beaches here, because they are being actively pushed upwards out of the sea, we tend to see bedrock cliffs. And the beaches tend to be pretty small. We get these small little pocket beaches are very common in this area as well. And that's because, again, the landscape is being actively uplifted and the sand is being actively transported away. Here's a profile from California down to the Pacific Ocean. We're not going to be doing California, we're actually going to be doing Washington State, but you can see in this case there's 15,000 feet of elevation change from the summit of this mountain in California to the bottom of the sea, and that's over 100 miles difference. Okay, so we call these types of coastlines, these active margin coastlines, emergent coastlines because they are emerging out of the sea. They're uplifting out of the sea. And so we get all these really interesting features, most of which we're going to talk about in the lab are things like sea cliffs, headlands like this one. We're going to talk a lot about headlands actually. We'll talk about sea stacks a little bit, but there's other things called the sea arches, tombolos, and these little pocket beaches here. Okay, and here's a picture in Hawaii of a nice example of a headland and a nice pocket beach sitting in this bay. Okay, so let's talk a little bit about how this forms. So here's a picture from Google Earth looking down. This is actually in Peru, which is also on an active margin. This is very close to the Andes Mountains, and here you'll see the same thing. We see a nice rocky coastline. Okay, so you want to get used to that sort of satellite view to sort of pick out the rocky coast. You're going to look at one of these in Oregon. Okay, so waves will attack this rocky coastline with similar vigor to how it attacks the sandy beaches. The difference here now, though, is that if you see in this picture, When the waves approach, just like we talked about, they break, and instead of transporting all this sand, they're actually eating away and eroding the base of the cliff face. And as they erode that away, it creates something called a wave cut notch, which you'll see right here. It also polishes off something called a wave platform, a wave cut platform. And as it chews away, this will just collapse by mass wasting. It'll just fall right down, and you'll reset your coastline. You'll have another sea cliff behind it, another vertical slope. Okay? So wave cut platforms and wave cut notches are things that you want to look at and think about in the lab today. Okay, and this can leave remnant arches, remnant sea stacks, and all sorts of interesting features along the coastline as well. You actually see this remnant one over here. These are just pieces of it left behind. Here's an example then of the evolution of a rocky coast. Now what often happens on a rocky coast is that you have these headlands sticking out, like a tongue or promontory sticking out into the sea. Oftentimes this is created by mass wasting. This little area, the bay area over here to the left, may have been an area of collapse, and all that stuff fell into the sea and letting this sort of stick out relative to that. Okay. Now what happens over time is because this is sticking so far out, the waves just naturally attack this preferentially over the protected bay areas. And so this little thing sticking out actually erodes very quickly, leaving behind these sea stacks, as you can see here. Now there's a more complex process at play here. You'll notice these arrows showing the water converging on the sea stack itself. And so I want to talk about why water actually does that. It looks like the water is physically turning towards the sea stack from both sides. And in fact, that's exactly what's going on. So here's a picture from California showing this process. It's called wave refraction. You might have heard the term refraction in a physics class at some point, but it's the idea that waves, it could be light waves, it could be sound waves, it could be ocean waves, they slow down when they hit a certain, when waves slow down, they actually change direction, they bend. So I want to give you an example of this. If you look out in this picture, look at this wave crest out here. Okay, look at this straight wave crest just off the coast. Okay, see it right there? It's relatively straight. It's coming at an angle. It's going this direction, and it's going to slam into this headland here. But I want you to pay attention to the waves on this side. Okay, so here they're straight across, right? But as you come towards the land, this area is shallower, the area closer to land is shallower than out here in the open ocean, right? So because of the friction between the shallow water and the waves, these waves start to slow down first. This part slows down first. This part's still booking along, going pretty fast. In fact, you can see the waves have not broke yet over here. They're still moving along without touching the bottom of the water, the seabed. Here they're breaking because they are hitting the seabed, and here they're actually already surfing, like it's actually surf, because they've already broken. So what that does is, as you continue down here, is watch what the wave front does. As the wave that's hitting the land slows down, the wave front bends. So I'm going to draw that for you with these guys here. Okay, the blue arrows indicate the slowest waves, the red arrows indicate the fastest waves. And as the blue ones slow down, and the red ones keep going fast, the entire wave front changes direction. And so as a result of wave refraction, or wave bending, it attacks the headland from all sides and chews this thing up very, very quickly. So if we go back to this picture, that's what these arrows are representing, is the wave refraction process. Okay, you'll examine that today in the lab as well. And that's what creates this shape. Now eventually the coastline trends towards being a straight coastline again, until another mass wasting event pulls a chunk of it down and opens up a new bay and a new headland for new attack. Okay, the very final bit here, I'm going on about 25 minutes, is that humans are constantly trying to stop coastal erosion. They're trying to basically prevent their homes and structures from falling into the sea, and what we would rather do, is actually preserve the beach by growing the beach and making it bigger. So we oftentimes put barriers to reduce beach erosion and to allow for beach deposition. And so you're going to examine these features called groins, jetties, seawalls, breakwaters today in the lab. These are all different kinds of things. These are also detailed in the 3 videos that I sent, so please watch those to figure out which ones those are. But essentially, and I'll talk about unintended consequences, but the groins are these things that are attached to the coast, perpendicular to the coast. Their intention is to trap longshore current to keep the sand blocked behind the groin. In other words, they're trying to build up the beach in some places here and trying to prevent sand from moving further downshore. A breakwater is a barrier that is parallel to the coastline and sticks way out into the water like this to do exactly what it sounds like. It breaks the waves before it can slam into the beach, preventing the beach from eroding. And in fact, what happens often is because behind the breakwater, the velocity is slower, you'll get this little accumulation of sand behind the breakwater. Okay, so here's just a picture of a groin. The longshore current is coming this direction, and you'll see that on this side of the groin, the sand is building up preferentially to this side. And so they're building this beach outwards by trapping the longshore current and trapping the sand being transported. And this side, it's being eroded. One place where people like to build these types of things, these things that are perpendicular to the coast, are where they're trying to keep a bay or a channel open. So here's the open ocean on the left. To the right is land, but there's probably a bay or a harbor back here. And so they want to keep the shipping lane here free of sand. And you see all the sand on this side. Well, so they built something called a jetty, which is basically they line the channel with basically rocks or cement or whatever, okay? And then the longshore current traps the sand outside of that jetty. And that prevents this channel from filling up with water. Or, sorry, filling up with sand is the essential reason for that, so that you don't block the pathway of the ships. Here's some nice breakwaters again, and you see the deposition behind the breakwater here, which I think is super cool. This is an area of slow water, so the sand is left behind. This is an area of fast water, so the sand is eroded. Seawalls are these parallel walls that are right against the coast. They're not sticking out in the water, and there's same principle here. Is the idea is they're preventing that wave cut notch from forming. They're preventing erosion of that structure. This could also be what's called riprap. So I want you to look in the distance over here. Oftentimes the cheap way of creating a seawall is just to throw a bunch of objects, in some cases boulders, up against objects like this, and that works to also dissipate the waves as they crash into the object. So here they've got both a seawall and riprap in one place. That's R-I-P-R-A-P is riprap. Okay, that's the end of the lecture. I'm certain I missed out on some things there that I'll talk about in the lab, so please watch the pre-lab videos from YouTube. The first one, Beach River of Sand, is absolutely essential, and you can watch the other ones at your leisure. Okay, thanks everyone.